Are all these interviews questions? What is?
Sorry?
Are these?
Pokemon.
Pokemon.
Well, no, we're talking about FPGAs.
Okay, I'm intrigued. What's the relationship between?
Pokemon and FPGAs are like peas and carrots.
Nobody likes them. What's the story? I am intrigued.
No, I was just saying that there's a hardware emulation done on FPGA.
Yes.
That you can actually play like old Super Nintendo games.
Okay, cool.
So.
But there's none for the PC or like a software version? Or?
Probably, yeah, but like the hardware, like actually,
bit faster.
you can push it onto your TV through HDMI.
Okay, cool.
What if you run that for an FPGA on an FPGA emulator on a PC?
There you go. Now we're like.
Well, you can synthesize a processor on the FPGA. You can run the software emulation on top of that. Or you can synthesize a processor. You can write a simulator for the processor on the processor. You can keep doing that forever and ever, ad infinitum, whatever. Yeah. And you can put a person in a box and you can say, here's the whole thing, you run it now, slowly.
Hole in the box, the hand comes out.
Yes. So as always, it's a pleasure to see you again. I didn't neglect the question about the project and the labs. Yes. Okay, we can take those. First about the distribution. So in all previous instances of this course, we were assigning 5% to the project, 15% to the labs. Okay. Now, I'll be happy to discuss if you prefer something different. Usually the thinking goes that there's a lot of effort that goes in the lab and people usually do well in the lab, so we rather do that. On occasion, if somebody does exceptionally well on the labs, I would have given them extra credit just because why not? I mean, that's the point. So unless there are any objections, we can stick to that. Or we can find some other formula. I would want the project to count for something regardless, so I wouldn't want it to be less than 5%. If somebody, for whatever reason, they didn't do particularly well on the labs and they do exceptionally well on the project, I'll be happy to change that in favor of the project, but not vice versa. That is, take the labs and you don't do any project at all. Does that make sense? Okay.
Why don't you take 5% off the final exam and make that the project?
If you give extra credits, essentially, that's not exactly the same, but it has a similar effect, right? You may end up with a grade that's 110 out of 100.
No, like, I mean, instead of 50, make it out of 40, the exam worth 45?
I don't think, I think we're going to run into trouble with respect to, there's this rules about closely supervised work versus not closely supervised work, which really boils down in our case, I think, to there's a written exam, there's a document that says this is what happened, there's no discussion about what has happened. There can be discussion on what is worth, but not what has happened. The projects and labs are, there's a big component where it's not clear what happened. You just talk to somebody, you said something, you did, and everything now it's lost in the ether, right? So there are some rules over there. I can find them out. I'd rather not spend the time on that. I think at this point we're just worrying about too much about, anyway, from my perspective. But I'll be happy to have a longer discussion on this. So we spend some time on real material today? Not that this is not important, I'm just saying, okay, good. So where are we? So it's going to be a little bit too late for some of the interviews, but we're going to be talking about caches again. And tomorrow, hopefully, we're going to be talking about replacement policies, which is what our overhead, which is what happens with the caches for. How do we decide who dies? Okay, that's the whole point. But before we go that, let's refresh our memory where we are and keep building up on the idea. So we talked about what caches are, and we arrived at the point where we now know that caches can be set associative, direct map, or anything in between. Right? I was doing examples where we have frames where the data payload is always 1 byte. And let's do one last example again. Let's say I have a two-way set associative cache with 4 blocks or 4 frames, 1 byte per frame. So this has the tremendous capacity of 4 bytes, and it's organized like this. So the two-way goes into the columns, and I have 4 frames, so every column will have there are 2 columns, and because I have 4 frames, there are going to be 2 rows as well. This is called set 0, and this is set 1. Okay. That's the bottom line. When I get an address from the CPU, this is 32 bits in Neosys case. The lower bit here is going to be my set index. And the upper 31 bits are going to be the tag. And as we discussed last time, we have a sequence like this. So if you notice, there are 4 distinct addresses there. It's one being a byte address, of course. And when we run this through the system, what's going to happen is this is going to be a miss because you haven't seen this before. As a result of that, we're going to go to the corresponding set and allocate the data. So because this address ends to a bit that's 0, this bit is going to be 0. It's going to go here. I can do it in detail, but I hope you all remember how this is done. I don't want to tire you with this. I want to go to something new. This is going to go to the second set now. Nothing's going to be there. It's going to be loaded over there. That's going to be a miss as well. Clearly, this is going to be a miss. You're going to go to the first set, set 0. You're going to search through that. There's going to be a block that's full, but it's going to have 100, not 200 where you're looking for. That's going to be a miss. A miss. For the same reason, search in the second row. From this point on, though, you go to 100. We're going to go here. We're going to look inside. We're going to find, and this is going to be a hit. This is 101, hit, 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 so on and so forth. So we're going to get 4 misses, and if this sequence repeats forever and ever, that's the only ones we're going to see. Fair enough? Now, what's inside every frame? There are 3 pieces of information. One is a valid bit, 1 bit that says there is something here. The second is a tag. This is 1 bit always. This is 31 bits in this case because it's a relationship between what's my address space, 32 bytes, and what's the actual data capacity. Here it's a single byte. That's what, sorry, how many sets I have, sorry, for the time being. Right, so, and then there's the data payload, which is 1 byte in our case. And we're going to change that soon. Fair enough? Now, this particular organization of a cache exploits, what's the problem? What did I mess up? Nothing?
One of the bytes would stand.
Set associative.
What would the set associative mean?
That when you go to a particular set, you have to do an associative search, which means you have to search a lot of things in parallel. That's what it's the terminology. That's what it means. The extreme case is the case where the set has only 1 block. That is called direct map because you don't have to search a lot. You just go to this and you say, are you it or not? Just one thing. The other one, so there is only 1 search action for 1 object. Associative means I have multiple things to look at the same time. And I could be anywhere.
So you would look at them all at the same time, like one time, not you wouldn't have to go through all of them one by one?
Look, the straight answer to that is in practice, we want to look at them at the same time. If the question is, can I look at them one at a time? Of course, but then your latency in the cache is going to be a linear function of how many you have to search.
Yeah.
And you don't want that.
So you can look at them in parallel?
You have to do, when the intention is to look at them in parallel.
Okay, gotcha.
Okay? So, all right, let's understand how this thing works, right? So, this is my cache, again. And remember, the idea here is I have a valid and target data, and this is the same, right? So this is set 0, set 1, way 0, way 1. I get an address from the CPU, which is A31 to A0. Let's pretend that I get a full address from the CPU. What do? I take only A0, and I have a decoder here that says, which set am I looking at? This is the set. So this is only A0 at this point. 0, 1. You go to this set, and you read the whole thing out. So right down here, I'm going to get a copy of what's inside my cache. So I'm going to get 2 frames. Valid tag data, valid tag data. Let me repeat that. In the beginning, there was nothing. You got a request from the CPU. It gives you 32 bits of address. This cache has 2 sets, all right? 2 sets. I take the lower bit, and I select which set I need to search within. Okay? I get that full row out. What do I do after that? I take the upper bits, which is A31 down to A1. There are 31 bits here. And I compare with this end with this in parallel. I do these two comparisons in parallel. These are 31-bit comparisons. They're really an XOR because I care to see if they're the same. Then I take this and that and I end together, this and that and I end together. This says hit way 0 because these are the ways, these are the sets. These are sets, these are ways. All right? So far so good? Set are these the rows, ways are the columns. You go into a set, you get all the ways for that set and you search for all of them in parallel. I got these two signals. Correspondingly then, based on that, I pass the right thing. I either pass this data or that data. That's what comes out. And how this is done is by using these signals as control. I will either pass this or that. Fair enough? Makes sense? Let's do one more example. Let's say this was a 3-way associative cache, but I had a lot of stuff in it. So this is now a 3-way cache, 1, 2, 3. This is way 0, 1, 2. And I have 1, 2, 4 sets. These are the sets now. This corresponds to 0, 0. This is 1, 1. How do I index this thing? I get an address from the CPU. I'll get 2 bits, which are going to be A1 and A2, the last two. That give me the set. Those give me the set, all right? So I'll go, depending on which address it is, I'll go to the corresponding set. I will pull out those 3 frames, 1, 2, 3. They have valid, tag, data. Valid, tag, data. Valid, tag, data. And I do the same now. I say, here's the tags. Let's put comparisons there, 3 of them. Here is the upper 30 bits because I already used 2 of them. A31 to A2. A1 and A0 tell me the set. Let's do a comparison with all of these guys in parallel. Then end with a bit, the valid bit. And I get 3 signals. And at the end now, I have the equivalent of a multiplexer that takes 3 inputs that are bytes. They give me 1 out. Which one depends on these signals? Everybody understands this?
That was really
Let's,
fast.
okay. I will take that not as a positive thing. Okay, let's go again. I get an address from the CPU. My cache here happens to have 12 frames. They're organized in 4 rows of 3 frames each. What is the associativity of the cache? Is the number of columns. How many frames you see on every row. This is a 3-way set associative cache. It could have been 4-way, 5-way, whatever you want it to be. These are the number of ways. How many sets is how many rows you have. What is the total number of frames? Rows times columns. Associativity times ways. So far so good? This thing has 12 frames. How does it operate? You get an address from the CPU. Anytime I go to fast stop me. 30 bits. Okay. Now, I take the lower 2 and I map, according to that, to one of the rows. Addresses that are directly divisible by 4, the lower 2 bits are 0, 0, go to the first row. Modulo 4, you find the row you go to. So addresses, if you divide them by 4, you have a remainder of 1, they will go to the second row, so on and so forth. What we do next is we pull out the full row. All 3 frames that are inside. We pull the whole thing out. How many? And what do we do next? We're saying we want to ask each of the 3 frames if they happen to have the data we're looking for. How do we find that out? We have to compare our address with the tag that's there. We don't need to keep the lower 2 bits because those were already used to index into the rows. So for a block, for a frame to be there, it has to be that its address had the same combination for the last 2 bits. That's not part of the comparison for the tag anymore because we know that's the identity. We do have by definition the same pattern on the lower 2 bits. We go now, we look at the upper 30 bits, the remaining ones, and we say, is this it? It. What are the options here? None of them are it. That's a miss. Or one of them hits. How do we compare? We take the tag, we XOR with the 30 bits we have. If the result is 0, this means that all the bits match. Okay. You could subtract it and see if the result is 0. That's a little bit excessive, but it's the same thing. You also end with the valid bit, because those bits exist here. In the beginning of time, there was nothing though inside the cache. So you got to say this block is empty. If the cache is operating correctly, and we can make sure that that invariant holds true, only one of them will match, if any. Two scenarios. One of them matches, hit. None of them match, miss. Once you find which column was the one that matched, you take the data from that column and you ship it out back to the CPU. So you respond that. And the whole point is that this process is going to be much faster than going to your off-chip memory, which is 50, 100 times slower. That's the whole point. Fair enough? In today's systems, that usually takes 2 to 3 cycles, sometimes 4. But it's still much faster than going off. And there's other techniques because of pipeline to hide these latencies. We're good? Okay, should I say this again or you start throwing stuff at me? Okay, alrighty then. So now we have an understanding of what sets and weights mean, right? So that we get a perspective. These are toy examples. Your typical cache capacities for level 1 caches, the ones that are next to your CPU, are going to be something in the order of 32 kilobytes. You're looking at caches that are typically 4 to 6 ways set associative, and they have tons of sets, of course, because you have to fit 64 kilobytes. But before I go and I tell you exactly how to derive how they're organized, I want to talk about a second phenomenon that programs have that I alluded to, I summarized in the previous lecture, that will allow us to get a better hit rate than this. Notice here that we never get a case where there is an address we haven't seen before and we get a hit on that. Never, ever. So you have to first see something, and then you have a chance of actually hitting to it if you happen to access it again soon. Fair enough? But as we mentioned last time, like in real life, in certain cultures and families, especially in mine, right? When you invite somebody, they bring the whole family along just because, right? That's a nice thing sometimes. Okay, so what programs tend to do is the following. We said the programs have a tendency of accessing the same data multiple times in closing time. There's a variable and we like it so much because that's why we declare it. We keep accessing it. It also happens that programs have a tendency to access nearby variables as well. This happens, for example, in arrays, because it's not a scalar and it's not a thing, it's the bigger data structure that contains many little things that you access close in time. So let's say you're scanning an array. You have an image, for example, you want to increase its intensity. This means take every value and multiply with a number, so it looks more bright. That's the one way of doing it. Fair enough? Another reason why this happens is because when we write programs, you tend to write programs, you say variable I, variable x, z, whatever, and you declare those close in text. Syntax-wise, they're close, and they're also conceptually close when you manipulate them. It's the same pieces of data that same block of data that you manipulate in a function. Am I making any sense to you? I think you're drifting away, so I'm going to move on, assuming that all of this makes sense. So, how can we take advantage of that? All right. I want you to approach caches as a prediction mechanism. Again, it's like a bet. Remember when we had the pipeline and we said there's the decode states. There's nothing else to do. How about we read 2 registers just because it's going to be, it might be useful for the next stage. Same thing for the multi-cycle processor. We said this is the second cycle. I'm going to be decoding the instruction. Well, I can just sit idle, do nothing, but I know most likely this instruction is going to reuse up to 2 registers. How about I read them? If it turns out that he uses them, that's a good thing because I read them in advance. If it doesn't, too bad. I did some extra work, so what? Fair enough? Now, what's the idea behind a cache if you think about it? You're saying, I know that programs tend to have temporal locality. That is, if I see the program accessing a variable, it is very likely that it will do that again. So I'm betting now with the cache that if I keep that locally in my cache, my bet is going to pay off because the program is likely to access this again. So because I guess that it's going to access it again, it finds in the cache, that's a good thing. You with me? So you can view that as a prediction mechanism now again. It's a speculation thing. You're speculating. You access that, chances are it's a good thing. We only took advantage of temporal locality here. But notice there is spatial locality too. And remember, spatial with a T. Right? When I access 100, I access 101. And that's close to 100. I could use the fact that I see an access to 100 as a strong indication that something is happening in that neighborhood. So maybe I want to get something that's close to 100. How can I take advantage of that? Right? So let's see now what caches do to also implicitly predict anytime you access something that you're going to access stuff that's nearby and take advantage of that. It's a very simple mechanism. Now, the important thing to realize with anything that you do in architecture and in computers is not to make it work for every single possible case. You just have to make it work in enough cases, so you get a benefit. And remember, programs do gazillions of operations. So if there is 1 in a million you don't do well, or 1 in 1,000, well, it doesn't really matter, because 1 in 1,000, guess what? As a percentage, is exactly 1,000th. It is nothing. All right, so without further ado then, after this very short introduction, I'm very happy with it, let me tell you what is the magical mechanism to do that. Remember the sequence, I'm going to be using that. Okay, now let's talk about memory now. So this is the 4 gigabyte address space. This is main memory. And it's 4 giga, all right? Now, I want you to conceptually treat this as groups. There's nothing in the hardware that does that. Just we, in our mind, are going to treat this in groups. We're going to say there's group 0, which contains addresses 0 and 1. This is, I'm going to call this blocks. This is block 0. Then addresses 2 and 3 is block 1. And if we keep going this way, eventually we're going to arrive at address 100. Who knows what's that? 512, maybe. And then 101. This is going to be another block. And then eventually we're going to arrive at addresses 200 and 201. That's going to be another block. Okay. Now, the idea now is when the cache talks to the memory, remember the cache is between the CPU and the memory now. CPU never goes to the memory directly. It only goes through the cache. When the cache talks to memory now, it will never talk in bytes. It will always talk in blocks. And that block is something you define as a designer. The programmer doesn't need to know that. It's not exposed in the programming language. It's not exposed in assembly. This is a design time decision. You say, when I go to the memory in the event of a miss, I'm not going to access just 1 byte because that's what the CPU is asking right now. I'm going to ask for the extended family. In this case, it's not a big extended family. It's a short one, 2 bytes. But you could do this with 4. You could do this with 8. And it's nice if the bytes are actually, the block size is power of 2. And everything I'm going to describe will assume that it's a power of 2. Because we're going to say it's really important for that to be. So the cache operates, it's a simple mechanism. OK, now let's look at these addresses here. What's common here? If I were to write these addresses in binary, you're going to see that they look like this. A lot of zeros. At some point, there's a 0001. And then 0000, 0000 for the first one. And the other one looks like this, 00001, 0000001, right? So you can already see that there is a common prefix. It's very long. This is common. And then there is a lower part that changes. By the way, you can view that this is the base address of the block. And this is an offset within the block. This byte happens to be a distance 0 from where the block begins. This happens to be a distance 1 from the block begins. If I were to write this down, the pattern would look very similar. The only difference would be that instead of 001 here would be 010, and then 00000000. That's for 200. Then the 2. And this is 201. Again, similarly, this is the common prefix. And then there is an offset within the block. That prefix, if you view it, this is the block number. If I were to write down 0 and 1 like that, you see that the upper 31 bits form the number 0. If I were to write down the 31 bits for this block, you'll see that they form the number 1. Who knows what this thing, I think this is, what is 256.
Sorry, where does the block start and end? Is it just everything except for the first bit?
The block starts at addresses, because I defined the block size to be 2. Blocks start at addresses that are divisible by 2, even. Okay?
So anything except the first bit?
Yes, the first bit has to be 0. That's where blocks start. And the block itself contains that byte and the next byte, because the block size is 2. If the block size was 4, blocks will start at addresses that are divisible by 4, and it will contain all 4 bytes that follow. Okay? The one that you're hitting and that. We're moving on? Okay. Right. Okay. Let's deal with this story. How can we organize our cache now? Let's take a cache that is two ways set associative as before, but now let's make the data payload a block as opposed to just a single byte. So I'm going to draw the same figure. Two sets, set 0, set 1, two ways, way 0, way 1. Right. Again, they do have valid, tag, and data, but now the data itself contains 2 bytes, not just 1, 2. So this thing is 2. There's byte 0, byte 1, and byte 0. So this is the frame. The frame contains 3 things always. It contains a valid bit, a tag bit, and a block container. The size of the last part depends on what's the block. The block is a fixed design time parameter. You pick it to be a power of 2. Let's see how we're going to search things through this. So the CPU is giving me an address now. It's 32 bits. How do I search this cache? What do we know from this? We know that the lower bit, 1 bit, because the block size 2, is actually an offset within the block. So that we have no bearing on finding which row we should be looking at. It shouldn't be part of the indexing of the cache here. Because once you find the block and you hit to it, that's going to be the one that's going to select which of the 2 bytes you want. But it won't tell you which row this may be at. We can take now the next bit. So this is bit 0. We're going to call that the offset. So write down on your notes that off stands for offset. This is the offset within the block. And we're going to take the next bit now to be the set. So we take this bit, we go to a decoder here, and we select which row it's going to be at. What we do as before, we grab out the whole row. So we're going to get out this data, way 0, way 1, valid, tag, data, valid, tag, data. And what do? We take the remaining bits. How many we have? 30 left. Remember, one will be used to select which of the 2 bytes in the event of a hit. The other has been used to select the set. What's left is 30 bits. So we take the remaining 30 bits and we say, is this the same as this, or is it the same as that? And again with a valid bit. This allows us now to select a particular block. So we have the same organization. Now we get a block that contains byte 1 and byte 0. But we're not done yet. The CPU is asking for 1 byte. What do we have to do? We have to select the right byte. So we go now to the last thing, which is the offset. And there's one last multiplexer here that says, I'll either get this, if that happens to be 0 or 1. Does that make sense? So this is a 2-way set associative cache with 4 frames or 4 blocks, where every block is 2 bytes. Let's do another example now. Okay, we don't have much time today, I mean. Do this slowly or go all the way in? Okay, let's be aggressive. Let's go all the way in, and then we can backtrack if we need to. Okay, now. No. Okay, let's do it slowly. All right, let's do.
No, just go.
Go?
Just do it.
All right, your wish is my command. Okay, let's see. Let's pretend now we have, let's see how we're going to do that. We have a 16 kilobyte cache. That's decent. Okay, good. We have 32 byte blocks. 32 byte blocks. And this thing is 8 ways at associative. Huh? How does it look like? How do we index it? What is it? Okay, let's see how we're going to do that. Now, when people give you this, they refer to the effective data capacity of your cache. That is, at any given point of time, how much data bytes it can hold. Of course, there are tags, there are valid bits, so the actual number of bits you need to build this cache is a lot more than that. That's from the programmer's perspective, how many variables in terms of bytes it can hold. Okay? Now, so we know we have some kind of a rectangle, because caches are rectangles, all right, that is made out of little bricks pieces. And we have the following pieces of information. They're giving you the following things. They're giving you the area of this, which is 16 kilobytes, right? This is the capacity of it. They're telling you the size of this, and that's 32, clearly, bytes now. And then they also tell you, oh, by the way, there are 8 of those, 8 columns. Now, to index this cache, that is, if I get an address from the CPU, I need the following thing. I will get an address from the CPU. This is address from the CPU. And it's 32 bits, okay? I need the following thing. I need an offset, which usually is at the very end, which is the following. Once I find the frame that contains the block I want, which is the byte that I care about. So far, so good? Then I need a set that says, okay, which of the rows should I look at? And then whatever remains is the tag, because everything else is uniquely defined by that, and you don't need to compare that. Does that make sense according to what we described so far? Now, what can we get from the get-go? We can directly get this. Why? Because we know the block size. It's 8. So that has to be 3. Because 2 to the 3rd is 8. So once you give me, you find the block that you want, which of the 8 bytes it is going to be given by that offset. The addresses are going to be of the following form. There's going to be a common block number. This is the 32-bit pattern. And then at the end, there are going to be all possible combinations of bits from 00 to 111.
Aren't the blocks 32 bytes?
32 bytes, you're absolutely right. So this is 5. Okay. And this is going to be X, 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 X. And it's going to take all combinations. Thank you for that. 0, 0, 0, 0, 0, up to 1, 1, 1, 1, 1. Okay.
Can you explain why that's 5?
Oh, because he can explain that.
There's 32 bytes. So how many numbers do you need for 32 bytes? You need 5 bits.
Oh, because you want each byte here.
So going back to this figure, if you remember, we said here's the memory space. Now things don't look like that. They look like this. Address 0 up to 31, it's block 0. Address 32 to 63, yes, correctly, is block 1, so and so forth. That's how we treat the things. And if I were to write down how these addresses look, they will look like this. A lot of zeros, and then 5 bits at the end that take the value 0, 0, 0 up to 1, 1, 1, 1, 1. And if I were to write this now like this, it would be 0, 0, 0, 0, 1, and then 5 zeros, the first one, up to 1, 1, 1, the last one. So this is block 1, but now it's a really extended family, 64 people. That's a lot of people. Anyway, okay.
That would be the offset, not the set.
That is the lower 5 bits are the offset. The upper bits is the block number. By the way, this is memory. It's not a cache anymore. We're talking about main memory. How do we treat, when the cache goes to memory, what is the thing that it gets? When we go to the cache now, of course, given a block from memory, we have to see which set we have to look for it. Which set this might be appear at.
And how do you know how many sets you have?
Well, that's the story. That's why we started. I tell you, we have 64 kilobytes of memory. We have, I gave you some, I mean, if you can treat this as like a little tiny math problem. I don't want to offend anybody, but at the end it's like primary school kind of level or maybe high school. But let's go through this a little bit so you can see the complexity of it. Okay? People, when usually on their lecture, they cannot think. You have, it's like a one-way thing. Somebody mumbles and then people listen. So it's not that hard, but work with me for a second. So you have a rectangle. You know the total area. You know how many columns it has, and you also know the bricks. Now, if you sit down, you're going to come up with a few simple equations, and I'm sure I'm going to embarrass myself when I try to write them down. That's going to tell you how many sets you have. Let's see. So this is the area, right? Okay, 64. So we have the capacity. And then we know the block size. If I divide this, I get the number of blocks that can fit in the cast at any given point in time. So I expressed area now as number of blocks. Okay. Next thing, how many sets can there be? Guess what? There is the number of blocks, and then every set has number of ways of blocks. Correct? That's it. That's the level of complexity here. So this is what it is. So let's do this together, and that's the part where I probably mess up. Okay. So capacity is 16 kilobytes. So it's 2 to the 14, correct? Bytes. What's the block size? 2 to the 5th. By the way, you don't even have to do division. Usually you just have to do subtraction, because it's powers of 2. All right? Okay, good. There are 512 blocks in this thing. Okay. Now, let's go to this now. So, equals 2 to the 9. And how many ways? 2 to the 3rd. So there are 64 sets. That's pretty decent. It's not that bad, right? So if we were to look at now how this cast looks like, so it is now written very well. Let me erase this thing in the middle, and then we can see how this cast looks like. And how do we index it? So, this is a big rectangle, bigger rectangle. It has set 0, 0, 0, 0, 0, 0 up to set 1, 1, 1, 1, 1, 1. So there are 64 of them. And then it has 8 columns. Way 0 up to way 7, correct? Now, when the CPU comes in, it gives us 32 bits. This is the address from the CPU, as we said. I think I have that written over there. Now, the lower 6 bits are an offset. 5 bits, sorry. 5 bits are an offset. Did I mess up anywhere there? No. Okay. 5 bits. That is the offset within the block. Once you find the block, that's the offset within the block that is going to give you the byte you want. Now, how many bits will I use for my set? 6. Can everybody see that 6? The number of the set? I can also write this here. We have 5 bits for the offset. Now we need to find the set. There are 2 to the 6 rows. So we're going to use 6 bits there. It's a bit early. And what's left? I need your help now.
Tag.
Oh, yeah, no, I need a number. 11, 21?
Something like that.
Huh? Give or take.
Around 21.
Yeah. Let's pretend 21 is correct. I think it is, but anyway, okay. Who cares? Alrighty. These are the number of bits that every frame needs to hold for tag. Everything else, it's either not relevant to the tag because it's an offset, or it's implied by the position of the block within a particular set. Fair enough? That's how the cast looks like. How do we access this? We first take the set. This is step number 1. So we take the set. And we get a row. Step number 2. We get a full row. Way 0 up to way 7. We get this out. Step number 3. Tag comparison. Step number 4. Block selection. So there's some multiplexer here. And step number 5, byte selection. And for that, we're going to use the offset. Okay? So set is the first thing you care about. You get the set. That's the first thing you grab your hands on. You go with the set, you start accessing the cache to get the row out. The row contains all ways. Next thing you do is you compare the tags. Once you do the tags, that allows you to select which data frame you're going to get, and then what block you want, that's where the offset comes in. Make sense? All right. Let me ask you a question now. Let's say I'm in set 0, 0, 1, 0, 1, 1, 1, 1. Don't hate me for this. That's the set I am at. And I find a block. So let me erase some stuff here. So this is a question for you. We have 6 minutes. Maybe it's good enough. And otherwise, we'll finish this tomorrow. So I go to set. What do you write there? 0, 0, 1, 0. 1, 1. Who wrote 8 things here? This is the set. And I find that the tag is, how many bits we said? 21. 0, 0, 0, 0, 0, 1, 1, 1. Question for you. Which is the range of addresses that are being cached in there? Which addresses That is the question for you. Okay. We do know that we have to calculate something that's going to be of the form like this. Right? We do know that the lower 5 bits are going to take the full range. So they're going to start from 0, 0 up to 1, 1, 1, 1. What else do we know? We know the set 0, 0, 1, 0, 1, 1. And we also know the tag, right? 0, 0, 1, 1, 1, 0. So what is the range of addresses now? Well, now we have to do a little bit clean up and write this nice so we don't get confused. So this is a 32-bit address. And let's try to write this cleanly now. So it starts from 0, 0, 0, 0, 0. That's the offset. And it goes up to 1, 0, 0, 0, 0. Correct? And I'm trying to write this, so these are going to be hexadecimal digits. Let's write the set number now. This is 1, 1, 0. That's another hexadecimal digit here. And then 1, 0, 0. Fine. And then we have the tag, which is 3 more bits. 1, that's another digit there. 1, 1, 1, and then a lot of zeros. So these are the hexadecimal digits. You see them? And let me copy them down here. 1, 1, 0. That's another hexadecimal digit. 1, 0, 0, 1. Another one, and 1, 1, 1, 0. And then all of them are zeros from top down. So what is the range of addresses?
Why do you have 4 ones in a row?
Where did I mess up? I tried to do this carefully. Maybe I messed up. Let's start. Here. The lower offset is 5 bits and it starts from all zeros. What's the set index? It's a 1, 1, 0, 1, right? Where did I get this extra 1 here? That's the question? Yeah. So this is, I think that's what you're saying. So I have had a 0 here. You're right. I messed up over here. I've put an extra 0. Yeah, correct. So let's write this down as hexadecimal now. I have another problem.
Why, at the bottom there, you said the offset goes from zeros to all ones. Why does it end at just 1, 0, 0, 0 there?
Because I'm saying things and I'm writing different things. Correct. Okay. So what is this thing? It's 0, 4, 6, 9, 3, and of course we have to write a lot of zeros in front of it. And what is this other guy? Is 0, x, 3, 9, 7, f. That is the range of addresses there. How much time we have left? Okay. Let's do one more question. I don't think that's going to be. So let's say I have this address in hexadecimal. If I get a miss on that, which is the range of which bytes are going to be brought in from memory? Again, let me repeat this. This is the address that the CPU is asking as a byte. Which bytes will I get from memory when I get a miss? Let's write this down in binary again. 0, 0, 0, 1 for the 1. 0, 0, 0, 0 for the 0. 0, 0, 1, 0. 0, 0, 1, 1. Correct? Okay. What do we have to do? This is the offset within the block. Correct? Everything else is the block number. All we got to do is we got to convert this to 0, 0 and go up to 1, 1, 1. So the lower address is going to be one that's all of these are zeros. And the higher address in the block is going to be one where everything is 1. Fair enough? So this is the totality of the bytes are going to come in from memory. Write this in hexadecimal, you can view it as a human better than you can view it in binary. That's all there is to it. All right. Yes?
So you seem to imply that everything one said maps to the same block.
As a byte in memory, there is a fixed set of other bytes that you belong to as a block. So the first 32 bytes in memory are always in block 0. The next 32 in block 1, the other 32 in block 2.
No, I meant like when you load stuff into the cache.
There is a specific row you may appear at. Which way within the row may vary, but which row you're going to appear depends on the set bits.
Right, but over there you said that that entire part becomes a block number.
That part becomes a block number, yes.
Right.
Because I'm referring to memory. When you go to memory, you go to your cache and you say, I want this byte. The cache says miss. Okay? What will the cache ask from memory? That's the question here. When the cache goes to memory, which bytes will it ask to give it? I think I'm failing to communicate what is the question here.
So, like, the address represents the cache includes a set number.
The address the CPU sends to the cache, it is a full 32-bit address. The cache internally splits this like this. You use that as a set. It goes internally, looks for that block. It doesn't find it, so it gets a miss. Now, memory doesn't care there is a cache. Memory can only respond to requests for reading a bunch of stuff. Yeah. When this thing goes to memory, because it has to fill in a full block, it will say, memory, give me all these bytes, because I need to fill a block.
So then everything that set is from the same block.
Everything in?
In that set is from the same block.
Everything in the set is not from the same block because there are 8 different blocks in the same set. The set is it's an 8-way set associative cache. Everything within the block is from that block. Again, this is an 8-way set associative cache. 8-way set associative cache. You get a block from the CPU, a request for a byte. It will fall into one block in memory. So I get again, sorry, I'm confusing you. I get a request from the CPU. Let's say it's for this byte. Okay? Okay. So this happens to be block 1. What does the cache do? It says, oh, block 1 happens to map here. First row. Second row. Yeah. Let me search through the 8 blocks I have internally. It's 8-way set associative cache. Yeah, it weighs 0 to weight 7.
Okay. So so what you push into the cache, would that just be 32 bytes?
Yes.
Or would it be 32 times 32?
No, 32 bytes. The cache operates at the individual level of the block. That's what it talks about.
So single block.
Yeah, CPU talks bytes, cache talks blocks. When the CPU talks to the cache finds a block and gives it the byte it wants. When the cache talks to memory, it says, give me the block, the whole block, 32.
So those 5 bottom bits refer
To memory would always appear 000.
So those 5 bottom bits refer to 32 different bytes that
Within the block, but that block is treated as a single entity. The cache will never ask for anything that it's a fragmented portion of that. We'll always ask that. Remember, this is the extended family. Why we're doing that? Because we're using that as an implicit prediction that if you touch any member of this family, it's very likely you're going to touch others too. So the cache says, oh, you asked for this guy in between there, this middle one? Well, let me get the ones before and the ones after. Which ones he gets, it doesn't depend on which element you touch. That's the thing, the simplification the cache makes. It doesn't say, I'm going to ask for the next 32. It just says, I'm going to ask for the group that contains you, and the division of groups is static. It never changes at runtime. You with me? So the cache doesn't do the following. It doesn't say, you asked for a byte, let me give you the next 32. It doesn't do that. It says, you asked for a byte. I already have a division of bytes in memory to groups. Let me give you the group you belong to. If you happen to be the first element, you'll get the next 31 too. If you happen to be the last, well, you get the previous 31. Which ones he gets, it's a pre-made decision. That's which group you belong to. And that's done for simplicity, so this thing works cleanly. All right, so thank you for your time again.